Hi everyone, in this video I'm going to tell you about another percolation model. This time this one is called oriented site percolation, and we are going to specialize from the beginning in oriented site percolation in 2 dimensions. So that's another example of percolation model, so it has a lot of similarities with bond percolation, so that's the stochastic process we studied in the previous videos. There are in fact a few differences, and mostly 2. And you can guess them from the name of the process. So instead of bond percolation, now we look at oriented site percolation. So bond in bond percolation means that edges are independently open or closed with some probabilities. The word site means that now we are going to look at percolation processes where sites are open or closed. So that's the first difference. Instead of having open or closed edges, we are going to have open or closed vertices in our graph. Now, the second difference is this word oriented. We look at oriented site percolation, and this comes from the fact that now instead of looking at percolation on some undirected graph, we look at percolation on some directed graph, meaning that now the edges are in fact arrows going in one direction, and the main consequence of that is that now instead of having paths of open edges, we are going to have a directed path of open vertices, and so those paths can only go in one direction. So that's the 2 main differences. Except for that, there are many similarities, and so now let's look at some more rigorous definition of oriented site percolation in 2 dimensions. So the first step is to give a rigorous definition of the directed graph we are going to use. So this directed graph is described at the top of this slide. The vertex set is going to be this set L, which is the set of xn in z cross z plus, such that x plus n is even. Z plus here denotes the set of non-negative integer, so that means that the set of vertices is in fact located in the upper half plane in Z2, but you see that that's not only half of Z2, we also remove some vertices with this condition x plus n even, and I'm going to explain after what this means. So then after we need to turn this set of vertices into a directed graph, and for that we need to draw directed edges or arrows, and in this case we are going to draw an arrow going from xn to x prime n prime if and only if x prime is equal to x plus or minus 1, and if n prime is equal to n plus 1. So the condition n prime equals n plus 1 means that all the arrows are going up, and the condition x prime equals x plus or minus 1 means that you have arrows going up right and arrows going up left. Now, before going further in the slide, I'm going to show you a little picture of what the graph looks like. So you have, let's say, the x-axis here. Okay, everything at the bottom is not of interest. The graph is all at the top. Then you start with looking at all the even numbers here. So maybe it's 0, 2, negative 2. And then this condition that x plus n is even means that those vertices just 1 unit above those ones are excluded from the graph. Instead, we are going to look at those ones. So those are the vertices of the graph. Now you look at distance 2 here, and again here, and again here. So that's what the set L looks like. That's the set of vertices that we are looking at. So you see that there are vertices that we don't count here, and the set of edges we are going to consider is just like this. So we have edges going that way, this way, and also going left like this, and you just keep going, and that's exactly the directed graph we are going to use to define oriented site percolation in 2 dimensions. So now after defining properly this directed graph, next step is to define oriented site percolation from this graph. Here I didn't write much on the slide because that's exactly the same as for bond percolation. The idea is that the the oriented site percolation process with parameter P is just going to be an object that I'm going to call Xi again, that corresponds to a collection of independent Bernoulli random variables with the same parameter P that we are going to call Xi xn for all xn in this vertex set L. So that's exactly the same definition as for bond percolation, except that now those Bernoulli random variables, instead of being indexed by the set of edges of the graph, they are indexed by the set of vertices of this new graph. Then, after we can, exactly like for bond percolation, we have similar definitions. We say that vertices or sites such that Xi xn is equal to 1 are open, the other one are closed, so they are going to be independently open with probability P and closed with probability 1 minus P. Then we are going to again define the notion of open path, except that now you see that there is a direction, like those paths can only go up. So we are going to write 0, 0, arrow xn to indicate that there is an open path going from 0, 0 to xn, and here by open path I mean a directed path of open vertices or open sites, and so of course you can only go up in the graph, so that's something very important. So now you have directed open paths that can only follow the arrows and going through those open sites. Then we can define the open cluster starting at the origin a little bit in the same fashion as for bond percolation, except that again now this open cluster cannot spread in all the direction. This cluster can only spread going up, and precisely the open cluster starting from the origin is again this object that I'm calling C0. Now it's the set of sites xn in L such that there is a directed an open directed path going from 0, 0 to xn. Then, same way as for bond percolation, we can define the percolation event and also percolation probability. So the percolation event, or the event that percolation occurs, is the event that the cluster starting at 0 is infinite, and the percolation probability is just the probability of this event. Again, that's some probability that depends on P that we are going to call theta of P. Finally, we have one more notion that we didn't see in the case of bond percolation, and the fact that we have this new notion comes a little bit from the fact that now we have an orientation. It's this idea of wet sites. So what we call the set of wet sites at level n, that's a set that we call Wn, so W for wet and n for level n, is going to be the set of integer such that you can go set of integer y such that you can go from x0 to such that there exists an open directed path going from x0 to yn for some x even number. So what this means is that we assume that at level 0, so that means the bottom of the picture, all the vertices are open, and now we are looking at all the possible directed open paths, so meaning again directed paths that only go through open vertices, and all the sites that can be reached from the bottom of the picture are going to be called wet sites. So here is a picture with two realization of oriented site percolation in 2 dimensions with 2 different parameters. And you see that in those pictures, I'm not showing the cluster starting at 0. I'm showing another aspect. We basically keep track of the set of wet sites. So I'm going to quickly explain how those pictures are generated. So first, we assume that all the sites at the bottom of the picture, so level 0, are open. For all the other sites, we just assume that they are independently open with the same probability P. And the set of open sites in those two pictures are represented by those white dots. Now, we assume also that at level 0, all the vertices or sites are wet, and the way we find the set of wet sites is by induction. Let's assume, for instance, that we were able to find all the set of wet sites up to level n. Then a site at level n+1 is going to be also wet if and only if we need two conditions. First condition, this site must be open, and second condition, one of the two arrows pointing at this open site must originate from a wet site at the previous level. So in particular, you see that being open for a site to be wet, being open is not enough, and in fact, indeed, in those two pictures, you see a bunch of white dots that are not reached from a path of like a white path starting from the bottom of the picture. So you see that closed site cannot be wet, but open site can be wet, but sometimes open sites are not wet either. Now, in terms of application, this process is of interest in physics, and to understand the possible application in physics. So first, let's imagine that those pictures are upside down. Now the lower half plane corresponds to a porous material, and now arrows are going down, which corresponds to the direction of the gravity. And you pour some water at the top of the picture, and the question is it possible for the water to keep on going down forever? So, of course, the porosity of the material is going to be modeled by this parameter P. If the material is very porous, that means that you have a lot of open sites, and so P is large. If at the opposite the material is not porous, then P is small. And clearly, if P is large enough, if you have enough open sites, then it seems that the water can keep on going forever. At the opposite, if P is small, the water is going to be stuck very quickly. And so in particular, you see that this interpretation really explains the reason why we call those processes percolation models. Now, the goal of this video and also the next two videos is to prove everything you see here on this slide. So we have three theorems. I'm going to prove the first one right now and the other two in the next two videos. So the first one, we already know this for bond percolation. It turns out that the result is exactly the same for oriented side percolation. That's the fact that the percolation probability is a non-decreasing function of the density of open sites P. That's not surprising. The proof is almost the same, but because it relies on some very interesting coupling argument, I'm going to quickly redo the proof, even if it's very similar to what we did before. Then, of course, from that, exactly like for bond percolation, we can define this notion of critical value, and again, we define PC as the supremum of P, such that theta of P is equal to 0. That induces like like this and the monotonicity of theta implies that there are two phases, so a subcritical phase where the probability of percolation is equal to 0, and a supercritical phase where the probability of percolation is strictly positive. And in the next two videos, we are going to prove upper bound and lower bound for this critical value. So, but right now, let's go back to the first theorem. So I rewrote the theorem here, and again, the proof is almost identical to what we did before, but in case you didn't see the previous video, I'm going to redo it here quickly because that's kind of a very interesting argument. So the way we prove that this function is non-decreasing is by using, again, what we call a coupling argument. So I'm going to start with that. That's the key. We want to use a coupling argument. So first we are going to fix P1 less or equal to P2, and so the goal is to prove that theta P1 is less than theta P2, and for that we are going to construct two realizations of oriented side percolation, one with parameter P1 and the other one with parameter P2, but in such a way that if there is percolation for the first process, then there will be, with probability 1, percolation for the second process, which means that those two realizations of oriented side percolation with different parameters are not going to be independent. They are going to form a coupling and they are going to be constructed on the same probability space. So to do this, what we did, and this still works, is we are going to define a coupling of one by one all the Bernoulli random variable that indicates whether sides are open or closed. So, and to define this coupling of Bernoulli random variables, I'm going to define that from a collection of independent uniform random variables. So, first step, I'm going to call u of xn. So instead of u of e, we don't have an edge anymore, we have a vertex, a side. I'm going to call u of xn, let u of xn be uniform in the interval 0, 1. All those random variables are also independent. Of course, those are indexed by, so all xn in the set that I call n, that's the set of vertices for the graph we are using. So we define those random variables, and then we can define ci, so I is going to be equal to either 1 or 2, so that's going to be those two parameters here. So ci of xn is going to be equal to the indicator function on the event that this random variable uxn is less or equal to pi. So, of course, because u is uniform in this interval, the probability that uxn is less than pi is exactly equal to pi, which means that this random variable is equal to 1 with probability pi, 0 with probability 1 minus pi. So indeed, this defines a Bernoulli random variable with parameter pi for I equals 1 and 2. Now, two things we can say. So now I'm going to write ci. So let me see here. So consequence of that. So ci, by ci I mean the collection of all the ci of xn, such that xn in this is in this set that we call L. So this is going to be an oriented side that's going to define an oriented side percolation process with parameter pi. So why is that? Well, because one, indeed, those random variables are Bernoulli random variable with the correct parameter pi, and second reason for that, we also want those ones to be independent, but indeed they are independent because they are constructed from those uniform random variables that we assume to be independent. So indeed, that's a collection of independent Bernoulli random variables with parameter pi, defined, like indexed by this set of vertices. And so indeed, this object is indeed, so I'm going to write oriented side percolation process, OSP, with parameter pi. So indeed, we were able to define the object of interest. And second condition, so those random variables for different values of xn are independent. However, C1 of xn and C2 of xn are not independent because you see here they are constructed from the same random variable uxn. And in fact, you can prove that for all xn, okay, by construction for all xn in this set L, what we have is that C1 of xn is going to be less or equal to C2 of xn. So indeed, the only way that's not possible is if this is 1 and this is 0, but then that would mean that u is less than pi, but also more than is less than p1 but more than p2, that's not possible because p1 is less than p2. So now we have our coupling of two oriented side percolation processes with parameter p1 and p2, but such that the set of open sites for the first process is a subset of the set of open sites for the second process. And so now let me erase here. So now from that we can conclude. So because of this inequality, we have that the cluster starting at 0 for this first process C1 should be a subset of the cluster starting at 0 for the process C2, okay? And now what we want to do is to prove again that the probability that this one is infinite is less than the probability that this one is infinite. And for that, exactly like we did for bond percolation, we are going to define this function, so phi, that is defined on again an object of this type, so that's going to be a collection of zeros and ones indexed by L. So I'm going to call that phi of C in general. Is going to be, so that's going to mimic the event that appears in this percolation probability. So I'm going to say that it's the indicator function on the event that C0, so the cluster starting at 0, but when the set of open and closed sites is described by C, so I'm going to write C0 of C equal infinity. Okay? And so now we know that this is true with probability 1 also. And so now let me erase this. Remember that C1 and C2 are indeed realization of bond percolation with parameter P1 and P2. And so next step is just to say that sigma of P1, so by definition it's equal to the probability, so let me write maybe P1 here, that C0 is infinite, but because C1 is indeed a realization of bond oriented side percolation with parameter P1, this probability is also the same as the probability that this specific cluster is infinite. So C0, C1 is infinite. Okay, so then next step is to connect like this probability with this function. You see that if I take C equals C1 here, like the event here is exactly that one, and if I look at the expected value of this quantity, okay, expected value of this indicator function, by definition, expected value of indicator function on an event that goes from like the construction of the Lebesgue integral, that's exactly equal to the measure of this event, and in this case, the probability of this event, which is exactly this probability here. And so this means that we can rewrite this probability as expected value of phi of C1. Now it turns out that this function is monotone, is a non-decreasing function with respect for the inclusion. So what I mean here, if you look at this function, that's clear that because this is included in this, then phi of C1 should be equal to phi of C2, okay? That's monotonicity of this function. But also the expected value is monotone, okay? If you have two random variables, x and y, with x less than y with probability 1, then expected value of x is less than expected value of y. So combining those two things, monotonicity of the expected value and also the fact that this function also is monotone, and indeed we have this inclusion with probability 1, then we can say that this is less than the expected value of phi of C2. But again, using the same reasoning, expected value, from the fact that expected value of phi of C1 is equal to that, you just go back and use the same reasoning to say that similarly the expected value of phi of xc2, because xc2 is indeed a realization of oriented side percolation with parameter p2, that's going to be equal to theta of p2. And so that's it. This concludes the proof of the theorem. We were indeed able to prove that for all p1 less than p2, theta of p1 is less than theta of p2. So indeed, this function theta, the percolation probability, but this time for oriented side percolation, is indeed non-decreasing.